So in this video we are going to talk about error analysis for Taylor series method. Suppose we have an initial value problem. This is the differential equation. X is the dependent variable, t is the independent variable, and this is your initial condition. So this is called initial value problem, right? So here we know that we find approximate solution for x using iterative methods, right? Using an iterative method, right? So in each time step we get an error, right? So for Taylor series method or the M, let's talk this in general case, right? So let's consider we find solution to this initial value problem using Taylor series method of order m, right? So suppose we are at here this time step tk, and the given approximate solution is denoted by xk, right? These are given, and xk is the next iterative, xk plus 1 xk plus 1 is the numerical solution after one iteration, right? And this one is the exact solution to this initial value problem, right? This is the approximation to this, right? So this is our problem. Then the local truncation error, right? You know that this one. So we consider Taylor polynomial. We throw away so higher order terms after k plus 1 term, right? We throw away all terms after k plus 1 term, right? So because of that we get an error. So this is the truncation error. It is called truncation error. So truncation error is defined by the distance between approximate and the exact value, right? So here we have a theorem for Taylor series method of order m. At step k, the local error is of order m plus 1. That is, the error is of order m plus 1. We have to prove that. So that means the error is bounded by m times h to the power m plus 1 for some bounded constant m. So this one can be proved easily, right? So this is your truncation error, right? So so we know that using the Taylor remainder theorem, right? So this one is equal to the highest order. So this is the highest order that you throw away, right? So you throw away all terms after m plus 1 term, right? So this one is the highest order, right? H to the m plus 1 divided by m plus 1 factorial modulus of x, m plus 1 derivative of x evaluated at psi. So psi is some value in between tk and tk plus 1, right? So we know that x prime is equal to f, therefore so the modulus of mth derivative of f, because f prime is equal to m, right? So mth derivative of f evaluated at psi comma x, right? All right, psi is a number, which is located in between tk and tk plus 1. Right? So if this one is bounded, let's assume this function is bounded, then the error, truncation error, is bounded by this number here, m divided by m plus 1 factorial h to the power m plus 1. So this means the truncation error is of order m plus 1, right? Alright, so we done that theorem. So this is locally, this is the truncation error in each time step, right? Okay, so we assume we have this this condition. We assumed we computed this approximation. Then we find this. When you find xk plus 1, you get this much truncation error, right? Alright, so next one, I think I have discussed about well posedness, right? So if the ODE is called well posed, if it is stable with respect to perturbations in initial condition, so that means we know that the behavior of x changes continuously with respect to the initial condition. So this means x of t and x tilde of t be the solutions with two different initial conditions. So we perturb the initial condition like this here, right? Then these are the two solutions for each initial condition. For this initial condition we get this solution, for this one we get this solution, right? So fix a final t, then there exists c, constant c, which is independent of t, such that this inequality satisfies, right? Modulus of x of t minus x tilde of t less than or equal to c times x0 minus x tilde, right? This means the solution is amplified at most by the factor of c, right? The solution, if you perturb the initial condition like this, the solution is amplified at most by the constancy. That's the thing. So this is your solution. When you perturb your initial condition, the solution is amplified at most by the constancy. That's the thing, right? So now we are ready to define the global error or total error, right? So here, so is the error at the final computing time, right? So here our independent variable is t, that's why we call t time, right? Let's say time t, right? So this is the number of intervals, subintervals, and per case n is the number of intervals, and t is the final time, right? I think you remember, you know this, right? This is your initial one and this is your final, uppercase t, right? And h is the distance of the grid size. So h is the grid size and t is the final value of your independent variable, and n is the number of subintervals, right? All right, so the total or global error is defined as this, so which is the exact value at this time and the approximate value, the distance between exact and the approximate value at this time, right? So there's a theorem. So assume that the ODE is well posed. That means there exists solution to that initial value problem, and the solution is unique. And what else? If you perturb the initial conditions, the solution is amplified at most by this constancy. That's the thing, right? All right. So if assume that OD is well posed, your initial value problem is well posed. If the local error of the numerical iteration satisfies this one, we proved this, right? Then the total or global error satisfies this. The global error or total error is of order m. So this is your local error. Local error is of order m plus 1. The global or total error is of order m. So for some bounded constancy where say C is uniform in T, right? Yeah, this means the order of the method is always one less the order of the truncation error. Yeah? The order of the truncation error is m plus 1. The order of total error is 1 less, right? All right, let's prove this one, right? The total error satisfies this. The total error is of order m. Let's try to show that. So let's look at this diagram. This is your time axis, t0, t1, t2, and this is your final t per case n, right? All right, we start off from here. So we know the initial condition at time t equal to t0. You know the initial value, so which is this x0, right? All right, x0 here. So this is the exact solution. This is the exact solution, and so using this one, yep, we find the approximate value at t sub 1, right? So this is the approximate one, this is your exact one. We started off from here, right? This is your exact solution, and using this data we found an approximation to this, and this is the exact value, right, at t sub 1, and this is your approximation, and this one is the error at this time step, right? Now we use this this approximated value here to find the next iterative, to find the next approximate value. So this is now the initial condition is this, and if you find the exact one, this one is the exact one, right? And look at this one here. So gap between exact and approximate is, this is the E, right? The error is E1. So at time step Tn, the error is amplified at most by the constancy. That's the thing, because the problem is well posed. The problem is well posed, so the error is amplified at most by constancy, right? So this is the error at Tn. Alright, now we use this as an initial value for the problem, right? Then we can find the exact one. So this is your exact value, right? Exact function for this initial value, right? This for this initial value, and this is the approximate one at time t2. So we denoted this one x2, and this one would be x of t2 for this initial value, right? This is the exact, this is the approximate for this initial value, right? So then the error is distance between exact and approximate. So at time t, the error is amplified at most by constancy. So this gap is less than or equal to c times e2. So this gap here is less than or equal to c e1. This gap is less than or equal to c2, and we use this initial, this approximate value. This is an approximate value at this time step. We use this value as our initial value to find the next iterative, right? So therefore we get, so this is your exact solution for this initial condition, and this is your approximate one. So for next time step t3, so this is your exact, this is your approximate is denoted by x sub 3, exact is x of t3. The gap between these two is e3. So this e3 is amplified at time tn. This e3 is amplified at most by constancy. This one is less than or equal to ce3. And if you want to find the total or global error, you have to sum this up. So we keep doing this process until here, right? Tn minus 1, right? Minus 1. So we keep doing this, then we get these kind of errors. So if you want to find the total error, you have to sum this up, right? Here, look at this. So yep. So we have to add up all the accumulated error at time t. So this is your final time. This is capital T here. So this is, yep, this one is same with t cap per case t. Yep. So if you want to find the total error at t, you have to sum this up. So sum this up. So this local error is bounded by this value, right? You can plug that one into here, and then so here k, so here all terms do not depend on k, you can take it out. So then this one is equal to sum n times uppercase n times cm divided by factorial n plus 1 times h to the power m plus 1, and n times h is what? N times h is final t, final time t. N times h, this is t. cmt divided by n m plus 1 factorial h to the power m. This is order m. Therefore, the method is of order m. Right, this is the proof. The total error, right? The total error is of order m. Hope you understood this.